MBA program. I don't know what that stands for, but it's a program that recruits very talented young physics students to come to the US to study. And then he got his PhD in condensed matter physics in 1987. And he's now a professor at the McGill University, named as a James McGill Check Professor at the same university. He has been very well known in quantum and nano electronic transport, and has been elected as a fellow of the American Physical Society as well as a fellow of the Royal Society of Canada. This research has received many Canadian national awards. Let's welcome him.
Thank you. Morning. Thank you very much. And so I will report to you our work on device modeling from atomistic first principles. So these are repetitive, actually. You want to basically, the question we want to ask and try to answer is that can we simulate a transistor fully atomistic without parameters? And without parameters, we put in a code. Actually, these parameters you have to be able to calculate. Okay, so all the material, device, structure parameters you have to calculate. We are extremely good at doing continual modeling for a long time, and the issue is that can we do the same from atoms? And so, so for students, why anybody want to do this? Okay, it is because we have a lot of new materials. People are interested, a lot of new concepts, a lot of new device principles, and so on. So the fact is that it's very hard to get reliable parameters. So if you can calculate them, it's very useful. So this is the reason that I think from yesterday's presentation, we learned many of these atomic details actually can change your device parameters. So we'd like to compute them. And so it's actually a very hard problem. So I will give you a quick introduction of what we do. And I'd like to first thank my collaborators. These names in yellow are collaborators here in the AOE Center. And I have many other collaborators. Jeremy Taylor, some of you probably have heard, a graduate student of mine, and he was the first to really do this AEGF DFT. And also, I have been collaborating with Wang Jian for over 20 years. And it's a long time and very fruitful collaborations. And much of the work actually are really inspired by this AOE work. So basically, it's a very hard problem to do if you want to do everything first. There are many issues. I just list a few that we have to solve before you can even try. One of them is how do you actually dope a system atomistic? And then how do you deal with disorder scattering? And we have to solve these problems. And then you have to get the band gap correct. If it's not correct, you can forget about this transport. And another very difficult problem is how do you solve large sizes? We're talking about, density function theory solves maybe 1,000 atoms these days, but you have to solve tens of thousands of atoms, and that's a very hard problem. And then how do you know the whole thing is correct? Actually, we are dealing with non-equilibrium physics, and so this combining this non-equilibrium statistical mechanics with some kind of harmonic is not all that clear whether it's absolutely correct or not. So you have to benchmark against known results. And this actually is a very hard problem to do. And then there are some lesser difficult problems, but you still have to solve. And so essentially this is a hard problem from atomistic first principles, if you want to do it without parameter. And so some physics considerations which we have been following this line of thought for about 15 years is the number one important thing is to determine the non-equilibrium density matrix. Okay, so this tells you the statistical information of the carriers. And that is exactly what is solved, actually, in engineering. You solve Boltzmann equation, classical or semi-classical. But it's a distribution which gives you the carrier dynamics. So it's absolutely important. In physics, we are very familiar of dealing with the homotony. We are extremely good at trying to dig out very detailed homotony, but in quantum transport at non-equilibrium, that is actually a case of accuracy. And most important thing is how do you determine this statistical distribution of the characters. So that's very important. The second thing, as I said, is the homotony. Hamiltonian gives me energy levels, and then how do you populate these energy levels is determined by non-equilibrium statistical mechanics. So that's why you have to combine these two, and then you are able to solve maybe transport. So we are familiar with Cavendish non-equilibrium Green's functions. So from theoretical point of view, this is the method that we use to derive formula. And then, so that's why we started by looking at this non-equilibrium density matrix out of this NEG. Obviously, there are some other ways of determining the density matrix. You will hear later a talk that Professor Chen Guanhua actually uses a time-dependent evolution of the density matrix by directly solving it, starting from the initial condition. Distant past, you can think that your system is at some equilibrium, and you turn on your non-equilibrium physics, and you can do the same kind of problem. Basically, these are the statistical mechanics. And then what kind of Hamiltonian you want to use is a personal taste. And we do effective mass, tight binding, and we have people doing DFT, Hartree-Fock, and we choose DFT, and we also do a little GW sometimes, but DFT seems to be a reasonable compromise. It allows you to do reasonably large system and reasonably accurate. And so this is what we have done. And I will also touch our work on tight binding, parameter generation later on. You can watch my time and so forth. Okay, so what is AEGFD? So simply put is that you use some kind of density functional theory looking Hamiltonian, and that calculates the Hamiltonian. So what enters Hamiltonian, what determines the terms inside this Hamiltonian is constructed at non-equilibrium. So we use this NEGF to construct density matrix that actually enters the potential terms inside this Hamiltonian. And it is self-consistently solved. I want to mention that this density functional theory, this is an unfortunate name that when we wrote the first paper, we used this name, which was not actually absolutely correct, because this density functional theory should be put in quote. The reason is that this is not a ground state theory. And density function theory was created to do ground state. But actually now what we have put into this Hamiltonian is a non-equilibrium density matrix. So it's not calculated at ground state. So this density function theory is just some kind of self-consistent field which allows you to determine the terms of the Hamiltonian of the device structure. And then because of this non-equilibrium nature, this DFT inside this NEGF is not variation. So you cannot solve it at variational method. You have to really directly invert a matrix, which makes this method very time-consuming and difficult to converge. And that is not because of mathematics, but is really because of physics. And we know that when we solve density functional theory, nobody really inverts matrices. You iteratively solve. It's because you have a ground state, you have some kind of target you can reach. But at non-equilibrium, that physics disappears. So you have to really solve accurately. And this presents a very difficult mathematical issue. And so it's just an unfortunate name that we picked at the beginning. But anyway, this is the way that we solve it. And then the issue is to calculate density matrix from this NEGF. How do you do this, and so on. All right, so this is the formalism that we established 2001, and then we've been developing ever since. So to do this problem with area of excellence, you have to solve semiconductors. You have to dope it. And immediately that we face a problem of doping and disorder scattering with atomistic technique. How do you do this? So I'd like to thank Dr. Yuki Koyuchi. He's a student of mine. He's not a postdoc at Princeton. And Professor Shapke in Beijing. He was visiting us. And then at the time we were discussing how do we solve this disorder scattering. And then Yuki did his PhD thesis with it, some of this earlier paper. But our fundamental technical development, the theoretical foundation, was only established this year by Eric. And all the theorems are proved and so on, mounted. So now we are certain that this technique called non-equilibrium vertex, non-equilibrium coherent potential approximation, non-equilibrium coherent potential approximation is absolutely on solid base. Okay, so what this is about. So suppose you want to dope a semiconductor with some doping. Okay, there are some reasons that you want to do this. the main reason we are interested is not only to dope it, but also to study the disorder effect. And so when you dope it, actually, if you just shift the potential, there are many ways you can shift. Okay, and if the dopant concentration is very small, that is not so bad. But if you have some edge roughness, surface roughness, and so on, and really atomic disorder, then you have to solve disorder scattering. And in that case, atomic calculation is really screwed. Okay, because you have to calculate many, many configurations, and each of it is a very big calculation, and then you have to average. And this makes atomic calculation of such kind of problem impossible. But so in literature, actually, you look at people don't do this. Okay, they just calculate one configuration and hope for the best. Okay. A lot of papers are published that way. So we tested whether you can just calculate one configuration or not. So there's a student actually did this calculation. He calculated 1,000 samples, and he found that every sample gives you a different result. So you really have to average it. Otherwise, you can get anything you like. So this is an issue. So what we decided to do is it possible that I derive an average physical formula, okay, and then I just calculate that formula once. If you can do that, then your problem is solved. So that's basically the idea. I will derive a set of transport, Green's functions and average Hamiltonian and so on, already averaged over the distribution of the randomness, and then I only calculate once. So that is a technique that we worked at. So this technique actually existed in the literature since the 60s by Solomon and these people, called coherent potential approximation. So this is a statistical sort of approach that you think, on a matrix I have some disorder. So instead of really putting sleep disorder, dopant or something, you ask, what is the statistical information? On each side, maybe 99% is silicon and 1% is phosphate. You do this statistical approach, and this is an effective medium theory which works extremely well. It's really established for a long time at the equilibrium. So this is the upshot is that you basically have to average your Dyson equation in some way and calculate these averages. But this is actually existed at the equilibrium for a long time. And then if you want to just calculate equilibrium conductivity or transmission coefficient, you have to average this transmission coefficient over the disorder configurations. And that actually has been done also in the 60s by Valicky. And this paper was absolutely wonderful, but somehow forgotten in the literature. And then how do you do this? So this are well established. As long as you don't do phase transitions, this method works very well. So if you are going close to a metal insulated transition or something, this will not work. Okay, but but we are not doing it, so this is okay. So what is really not known is how do you do this at non-equilibrium? Okay, so essentially we have to do a bit more. That I have to average, the average density matrix has to be calculated by averaging over this non-equilibrium Green function, and that is something new that Yuki did. And so basically this correlates your forward propagator with the backward propagator. So essentially you have to calculate some extra vertex correction to this Green's function. So basically what you do, the important thing is that this correlated average is not equal to the average multiplication. So it's not. Okay, so then by doing this average, you are going to get two terms automatically, actually theoretically. One describes the specular part of the scattering, the other is the diffusive part of the scattering. You get them beautifully. So this one you can see actually from the formula that you have electron with a Q coming in and Q goes out. And this one is Q comes in with Q prime goes out. So you have this momentum non-conserving components due to disorder scattering, and you get given very physically. So basically by doing these kind of things, you will be able to derive a set of formula, and that you only have to calculate once. Okay. So the essence, mathematical essence, is to break this average, the forward propagator, backward propagator, with a self-energy that you have to calculate. And this self-energy is done at complex contour on non-equilibrium contour. And yeah, you have to do that. And then it's reminiscent to dirty metal theory in solid state physics. But nevertheless, everything is reflected. The statistical information is also reflected here. And that you can actually put into some code and solve. So this is done. And then only this year we were able to prove all the theoretical formula, because this involves extremely complicated Green's function analysis. And then we have this paper on non-equilibrium coherent potentials. And the important thing is that this basically allows us to calculate the average of the conductance and the variance of the conductance. So we can actually calculate the variance as well. And then that will tell me, where you put the impurity, maybe your variance will be smaller or bigger or something. So it's very useful. And so I think this one put this theory into a very solid ground. So as a very simple application, we got some money from SRC to do this, is to look at interconnect roughness scattering interconnects of copper. And the problem there is that if you make this line very small, like 40 nanometers or so, your resistivity somehow is empirically known to double. And that is very bad for chip designs. So you want to try to understand how do you reduce this, or maybe you can reduce it, and so on. And so basically, this is an old problem from dating back to Sondheim and Fox. Okay, and this guy was this famous Russian spy who I think gave, not Russian, he's a German, and he gave secrets of nuclear weapon to Russians in the 40s, and he spent 10 years to 11 years in the jail. But he's a very famous nuclear physicist. And he has some old formula, which says resistivity is, if you have surface roughness, is somehow inversely proportional to the width of the film, and with some parameter p, which describes whether you have disorder scattering, you have diffusive scattering or not. Okay. So basically, this p is a parameter that you can calculate from this method that I just described. And of course, experimental people determine p by measurements and so on. So we can try this and calculate this p. So this work was done by Fellows, and so essentially, what our idea is very simple. That if you have disorder scattering, you have surface roughness, you're going to scatter your momentum, and which is bad for conduction. So maybe we can put some atoms on top and smooth out this surface roughness. Maybe you will have less scattering, and then you can improve your p. So if you look at this formula, when p equals to 1, this term disappears. You just have bulk resistivity. But if p is equal to 0, then this term is very big, and then you have the surface roughness. So this is a very empirical method, and so our engineering colleagues wants to know what is the p, so we can calculate. So what we do is to calculate this using this disorder scattering method, and then you determine resistance as a function of length, and from this slope you get the resistivity, and then you change the thickness of the film, and you get this formula. So basically, resistivity you can determine as a function of the concentration of the surface roughness. What does that mean? How rough it is. So if you miss an atom, if you have 1,000 atoms, you miss one atom, you have 1,000 of X. And then we have to do a large number of atoms. These are the largest one I remember was 8,000 copper atoms or something using this first principles method. And you can calculate resistivity as a function of X. And let's just look on the left-hand side. Anyway, from this resistivity as a function of X, then with different length, the thickness of the film, you can fit to see whether you get this P or not. Actually, you can fit very well this Fox-Sondheim. And indeed, it is inversely proportional to P. And from this fitting, you get a P, out of this disorder of some kind of model. Okay, so you can actually get this P. And I think this is kind of neat. And it's very useful. And then you can look at, is it possible that I put some barrier layers and reduce this, and make this P closer to 1 or not? So you can actually do that, and that's exactly what did by Fellows, and he was able to find certain atoms somehow will reduce this surface roughness scattering by smoothing the potential. At the beginning, we thought by smoothing the surface, the real atomic structure will do it, but it doesn't. Actually, the important thing is to smooth the potential. And so certain atoms can do that.
It's some kind of screen.
This method, screening is very
No. Yeah, but exactly smooth the potential, what does that mean?
it means that you want to have an atom, once you put on the surface, it mimics the copper. So a little bit like that. You can never do that experimentally with copper, because when you create a copper line, you always have some pore variation. So hopefully by putting some barrier layer, you can solve this.
What is the wetting? Is it of those metals?
Has to wet.
Wet the surface better than
Wet the surface.
than the refractors, is that?
Wet the surface, what you think is really fill these holes on the surface. But that actually
It's not
does
in your
not. No,
calculation.
it's not. We found that it's more important to look at the surface electronic structure, whether it's, so to speak, matches copper or not. So this detail is in that paper, and I will not, some discussions why some works, some doesn't, but I will just be brief here, okay? And so how much time I have? Time goes by quickly.
Yeah, you have about maybe 20 minutes.
Oh, okay. Oh my God. Okay. So the second problem we have to solve, that's just metal. Okay. But metal is useful. Okay. So now we want to look at semiconductors. So the semiconductor problem is really a very hard problem, that you have to solve the band gap problem. Okay. So in theory, in condensed matter solid state physics, what we do is something called GW. So this is our own GW. Okay. So if you look at the experimental numbers of this, GW allows you to calculate the absolute value of each of these energy levels. So that's why you can get the band gap, right? Okay, but then this is a calculating of some molecule. We calculate many molecules with our GW, and then the experimental values is this blue dots. You can find them here. And if you do LDA, you are pretty bad. Your result is wrong. And if you do Hartree-Fock, your result is also wrong. But if you do GW, our code actually gives you perfect agreement almost on each of these dots. So GW is very good. Give you band gaps and so on.
What does GW stand
It's a many bodies of the Green's function, Coulomb scattering, sort of correlated function, so to speak. Okay, but unfortunately, at least for our codes, we have to use 500 cores to do each of these dots. So it's very impossible to do if you have 1,000 atoms. Forget it. So this one is good, but it's not very fast. LDA is bad, but it's very fast. Okay, so if you look at LDA compared with measurement, it's not good. And GW is good. So that's what sometimes we have to do GW, we don't do GW. But basically, unfortunately. Until a few years ago, Peter Blaha, who is the creator of this code in Europe called WEN2K, he come up with a method which is by combining some chemistry techniques, and he called this modified Betti-Johnson LDA. So the calculation speed is like LDA, but if you look at the numbers, actually agrees with measurement to some reasonable extent, actually quite good. Okay, for many different kinds of systems. So this is not a fundamental theory like GW, but this one is a practical method, which is very fast, and give you reasonable results. So we're very happy to read this, and then we immediately implemented this technique. As I said, that the real fundamental theory are here, but this is a practical method which solves this problem. And for us, that's good enough. And unfortunately, this method is not a universal because it's not based on absolutely solid theory. It's a functional produced by some ideas. And so sometimes it works, most of the time it works actually, and then sometimes it doesn't work. So basically, it's something that you have to test. Okay. And then, so the first test we have done is by a student of mine. We have an experimental group who measures band gaps of this indium gallium nitride, and as a function of the doping concentration, and so this is. There are some experiments, and here is our calculation. As I said, we know how to dope this. Right? We can dope this X inside here, and then changes the band gap. This is for some solar cell work, and it works actually. So fortunately, we have a group of excellent researchers here in Hong Kong U, and they have calculated all the three files and, using this functional. And then if you look at all the band structures, and these are three, crosses are the experimental value, and you see that this functional can actually go through this and give you quite reasonable band gaps and band dispersion as well as effective mass. The effective mass for most of them is like 10% or so compared with the reported values. And effective mass is much harder even to determine experimentally. So within 10%, 15%, we think is good. So this is actually a very good technique, which is practical, and if you work hard at it, it will work. It has some caveat over there, and you have to gain experience. Not only that, Dr. Wang Ying here also calculated the band offset, and this is a much harder problem to do because so he did this famous heterojunction as a function of the concentration of aluminum, and then you will find that if you just look at aluminum gallium arsenide as a function of aluminum concentration, experimentally we know that around 38% of the aluminum concentration, the band gap changes from direct to indirect, and then with the transition looking like this, and you can actually produce them very accurately. And then the band gap, the alignment of this interface, both the conduction alignment and then the valence alignment, you can determine them in one shot. So a valence band alignment can be done because if you can forget about band gaps in the old days. But conduction band alignment, you can never really do it. And so this is the first time that we can do this as a function of the entire concentration. So this one tells you that at least on heterojunctions of semiconductors, this one works. And obviously that you can ask, does it work for Schottky barriers and so on. So we are working on those problems, and this is okay. I want to quickly go through this large systems. How large is large? So basically, if you want to do this kind of a silicon scatter, okay, your matrix is a milling square. Basically, you have to invert this kind of matrix. As I said, there is no variational principle. You cannot really solve it iteratively. You have to invert the matrix, and that actually tells you for large systems. So this one we have not been able to solve very nicely, and we just tried all the known mathematics and tried to solve it. But nevertheless, now with very good parallelization, we are able to solve about 10,000 silicon atoms. So that's something like that. Okay, each atom has 10 orbitals and so on, and you can actually do. So the computation speed, this is actually quite a few years old, and now it's faster than this. You're talking about maybe 40 minutes, you can get a step down in the self-consistent calculation, and your memory is limited to 3G per core, and you can parallelize, the whole code is parallelized, and you can actually solve some reasonable systems. So for two-group calculation, the largest one we solved is 19,000. So it takes several days, unfortunately, but at least it converges. Okay, so we know that this one can solve about 10,000 atoms. I would be very confident. Now, to solve a million atoms, you can never do this first principle. So you have to do tight binding. Therefore, we spend a lot of time to investigate how do we get very accurate tight binding parameters with transport emphasis, and so that we can actually predict transport. And then this is the largest calculation we have done is about 1 million silicon atoms, 10 orbitals per atom, and then with such a structure, it took 2 days to calculate transmission. And so on a 32 core, a single node 32 core machine, and which is reasonable. And I'll come back to tight binding. How do you generate these parameters and so on later? Okay. So finally, that we were very lucky to have Li Ning and Mangsong to tell us that what you have done is out of shit. You have to test. Okay. So we've been testing this for very long. So what we do is that they have access to Centaurus. So you can compare with this measurement, that experiment. You can cherry picking. And so that, it's not very nice, we said. So let's compare with people use it in electrical engineering. And we decided to test against this TCAT, the Centaurus or Synopsis. We know this one has its own problems, but at least for silicon, it can give you nice results and so on. All right, so what we do is that we use our atomic model using self-consistent with non-equilibrium coherent potential with the correct band gap, all of that. And then we compare with Centaurus, which does distribution, and so on. So I just showed one, and this is published this year. And then if you calculate this channel with the silicon channel in this kind of scale, in our calculation with this our code, red is we don't do real atoms because we do ab initio. This real boron, this real phosphorus, and then different doping concentration, and you see the potential basically are read to very high precision. It's very nice. These two goes together, and then we test some other things, T-FET and so on. But anyway, it looks like this method have captured the main physics. Of course, this is not perfect. There are some little differences, but the main thing. So we are confident that this technique, AEGF, DFT, with all this correct, this theoretical and numerical method put in there, can solve a real transistor.
Is it one-dimensional model?
This one is a one-dimensional calculation with a big slabs. So as Professor John mentioned, that we did a simulation of a strand, and how does strand changes effective mass, and how does that change transport, and that was summarizing all of these tests with the Centaurus. So summary is that we have solved some problems, and then we have solved this other problem as well, and then we can actually begin to think about what we want to do. So how much time do I have? 5 minutes. Okay, I will. This is Jesse because Jesse is in Mark Longstrom's group now, doing a postdoc, and this is his last project he did, trying to use this method to see can you reduce the source to drain leakage. Okay, so this is his idea. His paper is published here, and so basically this is the leakage is because your potential is not high enough. That's basically, if you make a very high potential, then it doesn't leak. But because you can only dope so much, so basically this potential is not high enough. So what he is thinking is that somehow suppose you can concentrate your dopant in the metal, and then your potential will be much higher, and then you don't tunnel as much. So this is a very simple idea, to just test whether this works. And then by doing this calculation, indeed, if you concentrate your thing, your doping in the middle of the channel, you actually the tunnel conductance is much lower than uniform doping. So this is the message that I don't know how to do it experimentally, but theoretically, this is a thing is that you can actually maybe reduce this leakage by doing that. Another, also Jesse's work, was we have an experimental group who measures, nano contact, or this metal-metal contact resistivity of that. What he told me is that when they have tungsten, when they have gold, both are reasonable conductors, but if you have this nanoscale contact, they become a very bad conductor. What is the reason? So this is kind of puzzling, and so Jesse took this and did the calculation. So what he found is actually this orbital symmetry, and now you think it's obvious, And then for gold, you have S orbital. For tungsten, you have a D, and they just don't couple very well. When you have a nano contact, they don't couple very well. So that this resistance is much bigger. And the factor of 4 to 8 depends on how you contact. So this is published over there. And so these are the things that you can do. And we are interested in this transition metal dicarbogenites. And so basically, over there is a physics problem. We try to see whether we can use electric field from outside to tune the spin. Okay, so electric control of spin is holy grail of spintronics. And the reason for this material is possible is because this spin-orbital interaction is very large in this material. Okay, so basically this says my spin is oriented by this term. Okay, this term is like an effective magnetic field. And this effective magnetic field actually depends on the potential. So the potential is given by these atoms, but I can put an external potential to affect the spin. So basically the idea is that I can put a gate voltage to gate the spin, and that's kind of a strange, actually, when you think about it. Electric field controls spin. So you make a field effect transistor, you put an external field, and that actually changes the spin orientation as the electron goes through the channel. And whether then when they exit, it will depend whether this outside spin is parallel or anti-parallel or with some angle. And this is very much like data transistor, actually. The only thing different is that here I've got very strong spillover interaction, which can be controlled by external, this material itself has spillover interaction, instead of everything is induced like that. But anyway, you can actually calculate, I don't want to for IV curves. The important thing is that you can calculate something they call the valley curve. Okay, this material has two inequilibrium values, which is like a quantum index. Not only you have spin, you have two index, you have valley. Okay, so you can calculate what is the valley curve and so on. And then we have Professor Qu Xiaodong here did beautiful experiment, and Yao Wang did a very beautiful theory about this. So our work is motivated by their work here. All right. A few words about type binding. And we, as I said, we can solve maybe 10,000 atoms. We solved 8,000 copper, 19,000 silicon spheres, and so on. But that's the ballpark with AEGF, DFT at this moment. So if we want to solve larger systems, we have to develop type binding. But type binding parameters, usually you fit total energy, which is not good for transport. And then you have to fit transport, you have to fit the band structure, and that's harder to do. So we developed a code which does this fit. So you calculate the good band structure, and then discretize your band structure with many, many points, like 40,000 energy points. And then you have a 40,000 parameters you have to determine by optimization of your type binding parameters. So you do that, you can get excellent results. And Fedos and Leo did this for molybdenum disulfide, and you can see that these two curves, blue and red, they agree perfectly for one layer, two layer, and bulk, and so on with the same set of parameters fitted this way. And then this goes into our transport code, and you can calculate the transport. And we did all of this actually I just took a look on the airplane here. We actually have data for all of this, yellow. So we have all of it. And so this is it's a lot of work, but somehow for our own research, we need certain things we did fit it. And we also fitted all of these compounds very accurately. Many of these compounds are fit in one shot. So these parameters have certain transferability. And so right now what we are focusing on is to fit certain parameters that can be applied. We can apply this AECPA, this disorder step. So we have to fit these type binding parameters which include this disorder effect. So that's what we're doing right now. And so once we can do this, then all of this development in the past 4 years can be applied to type binding. And I think we're very close. Actually, we have a set down already. So we should be able to do this very quickly. Okay, so the summary is that by solving these kind of technical problems, we reached to a stage where I think we can solve some realistic problems with realistic physics, and we captured the main physics of this device modeling, I think. And we have others, electron photon, and scattering, and some correlation, transient current, all of this can be done within this formula. We actually have done them as well. Okay, so let's say there's many applications, but what do you do as a physicist? So we'd like to listen to people in this field, electrical engineers, people working in the industry, that we can maybe collaborate on this. And so this is, we can, at this moment. Okay, thank you very much, and I want to thank my Canadian funding sources, SRC, and University of Hong Kong, which I always spend many months here. So, thank you very much.
Thank you very much. Now is the Q&A session.
Yeah.
I'm fascinated by the result you mentioned about the conductivity of wires as a function of different metallic coatings. And I'm wondering, it's a long question, I suppose, but is the effect structural or is it electronic? I mean,
It's electronic.
It's electronic. So is it the same thing you were talking about with the contacts, where the gold tungsten contact, it's an orbital mismatch in the
That's what we are leaning toward. Because first, when we want to coat, we thought, we have to select atoms with similar size. And somehow it doesn't work very well. And then we found some other which does not seem to have the same size but work better. So then we studied, Fedor studied the electronic structure and found the density state at a Fermi level to be closer to copper is important. And so that's what we found.
And it's nothing to do with miscibility or any metallurgical property. I mean, because obviously this is theory. You can look at anything.
But this is small. This concentration, when we say, 10%, it's not really in the. I think we are inside the miscibility gap, or yeah.
Your calculation doesn't not relaxing atomic positions area.
So in this one, we did not.
Yeah, so that there's no.
So there is this discussion does not end.
But it might be that the miscibility properties actually follow from the electronic behavior that you're seeing.
That's also of course the surface energy you have to surface tension and stuff will end. Yeah, you're right. And right, to do structural calculation as well as this disorder is another level of complication. Right.
Well, I mean,
And we actually do sometimes.
But if you make a perfectly flat surface, what you've done is you put some disorder in to produce a scattering, right?
Yeah.
With a perfectly flat surface, then you get some specular reflection. Right?
Yeah, that's right.
And so what you've done is you put deliberately some structural.
I removed some copper atoms.
You randomly,
Randomly.
and then you randomly
And randomly put
fill
in.
some again.
That's right.
The
Yes.
same ones.
The same places. Yes. Yeah. So basically, yeah. I'm on.
Hi, yeah, very, very impressive presentation. You mentioned briefly Schottky barriers, and just can you comment on this? You had great
Yeah.
success with band offsets. Is the Schottky barrier problem more difficult?
My feeling is more difficult. Okay, at this moment, we have Wang Yin here is working on this, and then one thing is that we can, yeah. What we are doing right now is Schottky barrier. The thing for atomic calculation is that if your dopant on the semiconductor side is not high enough, you have a long tail, and you have to solve a huge number of atoms, and that just is very hard to do this way. So right now, what we're doing is to dope this very heavily, like turn to the triangle, really make it short, and then I believe we can actually do it. And but we have not done it. So we are working on this. Okay. So we want to solve this Schottky barrier problem, and within this formula. And then I think we then have all the pieces sort of ready. Yeah.
But even that problem of the contact resistance, that's a big challenge for semiconductor technology. You could find ways to lower that contact resistance.
That's a very good suggestion.
And how about phonon, electronic phonon
Yeah.
scattering? Is that
Yeah.
part of it?
We have done electron-phonon scattering. Self-consistently, if you do electron-phonon self-energy, self-consistently with the electronic homotonic, then you can only do a small molecule. So that's what we did, in 2005 or something to solve this. But through that exercise, what we found is that this self-consistent calculation, the phonon, will give you 20% more accuracy than not self-consistent. So what we decided now to do is just to do non-self-consistent. And so I have a student right now taking this self-consistent boron approximation and just take a piece out. And then because we know we have an accurate method, we can test how good it is. So that's what we're doing for electron. And for electron photon scattering, this is several kinds of things. And so we have a very accuracy, but now we don't want to do that because it takes forever to do even a very simple system. And for electron phonon, in one dimensions, we read the thesis of Jim Wu and many of this, and so I think we have a understanding how accurate this non-self-consistent phonon scattering will be. So it's quite good, I thought. The first one up to me is good enough for many problems.
Maybe you can postpone the discussion of coffee break. There's a lot of interest in this work.
Yeah.
Let's move on.
Thanks.